Well, let us start climbing the distance ladder. First, we'll talk about methods that we can find distances to nearby stars or star clusters. The trigonometric parallax is the most basic measurement of distance in astronomy, and hopefully all of you are well familiar with it. It is pure geometry and there is nothing uncertain about it. So by measuring the annual apparent sloshing on the sky of a star, we can figure out how far it is if we know the distance between Earth and the Sun, which we do know with a great precision. So the method by itself is safe. The problem is that these are very small angles, and the current state of the art is that we can measure distances using parallaxes to about 1 kiloparsec out, more or less. And that's well within our own galaxy, never mind external galaxies. The next one is so-called moving cluster method. This is a statistical method. Stars do come in clusters. Clusters move relative to the solar system, and stars have internal motions within a cluster itself. Since ostensibly all cluster stars are moving roughly in the same direction, if we look from afar, we'll see them converging towards some distant point, which is the direction in which they're going. By measuring the spread of those angles, we can figure out what's the angle of their actual velocity vector to the line of sight. We also measure proper motions of stars in angular seconds per unit time on sky, as well as the radial velocities. We can assume that random motions within a cluster are same both in radial and tangential direction. So by knowing what the angle is between the radial and tangential components, we can figure out what is the parallax to the cluster. Note that this makes some assumptions about internal motions of the cluster, and it is basically a statistical technique. So the more stars you have, the better, but clusters have finite numbers of stars. By measuring distances to a number of stars using either one of these two techniques, we can calibrate the Hertzsprung-Russell or color magnitude diagram for stars. Hopefully, this is something you know about very well. It is a plot of stellar luminosity versus temperature. Temperature is sometimes measured through color. The important thing to note here is that stellar luminosities are distance dependent according to the inverse square law from given measurements of apparent brightness. Temperature measured from spectra or from colors is not. Star will have exact same temperature no matter how far it is. So once we calibrate the main sequence on this diagram, if we can measure stellar colors or temperatures, then we can read off their absolute magnitudes. From absolute and apparent magnitudes, we can find out how far they are. In a given cluster, you may have thousands of stars, and therefore you can determine the distance very precisely, the distance to the cluster itself. Now, this works fairly well for young stellar clusters in the galactic disk. However, no globular cluster is as yet close enough to measure parallaxes to it, and so something else would have to be done about those. There, what we do is we use field stars of the same type as those that live in globular clusters, the population 2 stars. HR diagram measurement is a collective measurement, but not all stars are created equal. Between the temperature luminosity plane, there is a strip within which stars are unstable to pulsation, so-called instability strip. On the main sequence, those would be the Cepheids or delta Cephei stars. Among the globular clusters, horizontal branch, those would be RR Lyrae stars. There are many different kinds of pulsating stars, but those are the principal ones. And indeed, physics of Cepheids and RR Lyrae is probably the best understood of all of them. It turns out that there are correlations between observed period, which again does not depend on distance, and luminosities of these stars, which do. Those are empirical relations, and they can be calibrated if you had distances to a number of these pulsating stars using one of the previous techniques. At first, people did not know that there are different kinds of pulsating stars. They all thought it was one kind. And the first star that Hubble figured out in Andromeda was a Cepheid, pulsating star, that produced the first distance to another galaxy. But people were confusing RLARI, which are much dimmer than Cepheids, with Cepheids themselves. And that confusion led to an error factor of 2 in the distance scale. Once Walter Bade understood that there really are 2 different kinds of period luminosity relations, that error was corrected. Let's talk about Cepheids in more detail, because they remain among the most important distance indicators altogether. They're young luminous stars, therefore they'll be found in star-forming disks and star-forming regions, whereas Delta Cephei itself is a relatively bright one within our own galaxy. It was Henrietta Leavitt working with Harlow Shapley who recognized that there is a correlation between period and luminosity as they were studying stars in the Magellanic Clouds about 50 kiloparsecs away. Since all of them were roughly at the same distance, apparent magnitude would correlate with period. And then they understood that comparing that with nearby Cepheids, they can find out how far the Magellanic Clouds are. Cepheids are important because they are bright, and so we can see them far away. We can find them in galaxies up to maybe 25 megaparsecs or so. So we can calibrate distances to a number of nearby galaxies using Cepheids, which is not easy, but it's possible. And then we can use distances to those galaxies to calibrate some other relations. It isn't all perfectly safe. The pulsation of stars must depend on their internal composition and opacity, and therefore metallicity. The exact effects of metallicity are not firmly established as yet. Moreover, there are external problems such as extinction. Cepheids are found in star-forming regions, and they also tend to be dusty, so one has to make a correction for it. In very distant galaxies, they may be blended with some other stars, giving us wrong luminosity. Cepheids remain keystones of the distance scale, and that also applies for the measurements with the Hubble Space Telescope. Here are some examples of Cepheid period luminosity relations in Magellanic Clouds in different filters. The scatter is biggest in the blue band and the smallest in the near infrared. However, the amplitudes are biggest in blue and smallest in near infrared. It's a good idea to observe them in different bands so that the effects of extinction can be taken out. Until Hipparcos satellite flew, we did not have parallax calibration of Cepheids. Distances to Cepheids until then were based on the distances to clusters in which they live. And distances to those clusters were by and large determined using the moving cluster method. However, with the Hipparcos, a handful of Cepheids was within reach, and these are the actual calibration relations for distances to Cepheids. As you can see, they're fairly noisy. But in any case, for the first time, they gave us an absolute calibration of the period luminosity relations for Cepheid. This is going to get a lot better with the Gaia satellite, which is an astrometry mission, which will measure Cepheids to a much larger number of pulsating stars with a much greater precision. The other important kind of pulsating stars are RR Lyrae. They're also named after the prototype star that was first recognized. They are the population 2 stars. They're not on the main sequence, but on the horizontal branch, which is the helium-burning main sequence, and they're found in old stellar populations, such as globular clusters. They do have an advantage that their periods are short, so it's much easier to observe the full periodic pulsating curve for an RR Lyrae star than it is for a Cepheid. Because they're dimmer, they can be really used only within the local group of galaxies. But that's still useful, and it provides a welcome check on the distances measured using Cepheids. Now let's take a closer look to what happens when a star is pulsating. Its photosphere expands, but temperature changes as well. So the radius changes, the temperature changes, therefore luminosity must change. If we observe star spectroscopically, we can observe the velocity of the photosphere. It comes towards us, then goes away from us. So we can measure stellar temperatures using colors or spectroscopy. We can measure velocity of the pulsating photosphere using spectroscopy, and we can measure changes in the apparent brightness. This forms the basis of so-called Bade-Wesseling method. If the pulsating stars were perfect black bodies, this would be an excellent, pure physics-based method to determine distances to them. Unfortunately, real stars are not perfect black bodies. but they're not too far either. So at any given time, the flux from a star will be its luminosity, which is in itself given by Stefan Boltzmann formula. It's proportional to the temperature to the fourth power and to the surface area of the star, which is proportional to the square of its radius. And it's inversely proportional to the square of the distance. We can measure those quantities all throughout the pulsation period. So temperatures are directly observable from photometry. So are the fluxes. And the only remaining question is, can we find out the radius? We can, in a way, because if we integrate motion of the photosphere as traced by the radial velocity, we can find out how much the radius has been changing. So we have 3 equations and 3 unknowns, and we can solve for that. Therefore, we can obtain distances purely from measurements and assumptions about blackbody nature of stellar photospheres. A problem is that stars are not perfect blackbodies, and some modeling of stellar photospheres has to be done in order to actually make the method to work. So there is model dependence, and that's where the uncertainties come from. There are a couple more statistical methods that are based on stellar indicators. Globular star clusters themselves have a distribution of luminosities. It turns out that their distribution function, the luminosity function of globular clusters, seems to be universal among galaxies for reasons that are not really well understood at all. Actually, we can think of many reasons why this shouldn't be the case. But empirically, they do seem to be very similar. Thus, if we can calibrate the luminosity function of globular clusters in the Milky Way using local distance indicators, then we can apply it to the luminosity functions of globular clusters in other galaxies. The good thing about this is that globular clusters are much brighter than most stars, and so they're easier to find and easier to measure. Now, one problem is that the numbers of globular clusters vary widely among the galaxies. Elliptical galaxies, early type spirals, have most. Late type spirals hardly have any, and therefore there'll be statistical uncertainty for those galaxies. A similar method uses luminosity function of planetary nebulae. As you recall, planetary nebulae represent stellar envelopes that have been shed by a star following its horizontal branch phase. They're illuminated and ionized by the incandescent core that remains, and most of their light emerges in recombination emission lines. A very prominent line among those is a line of ionized oxygen at 5007 angstroms. We can measure luminosities of those lines alone, and then we can form luminosity function, that is distribution of luminosities, for that emission line alone, for planetary nebulae. That too turns out to be more or less the same for the nearby galaxies. Ostensibly, that reflects the way in which stars evolve, but there isn't really solid, strong physical basis. This is an empirical relation. And again, it is statistical. It can work up to the distance of the Virgo cluster, which is not so bad, but not beyond. And finally, there is the tip of the red giant branch. The stars cannot get more luminous than a certain amount. This is related to the so-called Eddington luminosity, which hopefully you have heard about and which we can address later. So empirically, they don't seem to get brighter than a certain limit. And if we can observe stars in other galaxies, nearby galaxies like Andromeda, and find out what are the most luminous ones, where does the luminosity stop, then that threshold can be used as a standard candle. The advantage of this is, of course, that these stars are bright. The disadvantage is that it's not a terribly well-defined indicator. There aren't very many of those stars, so the numerical fluctuations can affect the result. That is it about the stellar distance indicator. Next time, we will talk about so-called distance indicator relations for galaxies.